Have your attention, please. From 10 o'clock, we'll begin the 12th Space Weather Conference. Distinguished participants, please make your way to the conference hall and be seated. And please turn your mobile phone into vibration mode or turn it off. In today's conference, we provide simultaneous interpretation service for Korean and English. You can use the receiver on your table. Korean is channel number 1 and English is channel number 2. And for your safety, please keep your mask on during this conference. And this conference will be live streamed on the YouTube channel. And please refrain from using the vulgar language on your chat box. And in the case of emergency, please follow the guidance of the staff members. Then we'll see you soon. Thank you very much. We would like to begin day 2 of this conference. Distinguished guest, good morning. We would like to begin day 2 for the 12th Space Weather Conference. My name is Lee So-yeon. I will serve as an MC for today's conference. And in order to have more audiences, we are streaming this conference on YouTube channel. I would like to extend my appreciation to all the distinguished participants who joined us online and offline. And we look forward to seeing you until the end of this session, and I hope you can get useful information and insight through this conference. Then we would like to begin session number 2. The title of session number 2 is the space weather in the new space era, and Mr. Park Ji-ung, the researcher, now will serve as a moderator. Let me hand over the microphone. Hello everyone. My name is Park Ji-ung. I'm a researcher of Korea Space Weather Center. As for the session 2, we have 4 speakers, and each speaker will have in total 25 minutes. You can spend 20 minutes for presentation and 5 minutes for Q&A. And the first presentation will be given from Professor Sun Jong-ho, who is leading the NASA Artemis project. Please welcome him with a big round of applause. Good morning. Can I take off the mask? Should I keep it on? It is my pleasure to meet all of you. My name is Sun Jong-ho. I'm from Gyeonggi University. As you heard, I'm participating in the Artemis project, so I would like to introduce the space weather monitoring system. Even though I'm the presenter, it is a collaborative research. So we have Gyeonggi University, SATRIC-I, and the Korea Space Research Institute. So these are the order of the content. As you know, there is a CLIPS or CLPS project, so let me introduce them. Several days ago, the launch vehicle was successfully launched for Artemis. So this will be the first human lunar exploration project since the Apollo project. So we will establish the space station on the moon, and that will be used as an outpost for the Mars human exploration. And Canada, Korea, and US and 20 countries are participating in this project. And there are multiple elements in this project, and I would like to explain this area marked in the dotted red area. And on the left side, you can see the launch vehicle, and on these vehicles are required to reach to the moon. And on the right side, you can see the commercial lunar payload service, which I will explain. And on the surface or on the orbit of the moon, we can use multiple elements. Also, on the surface of the moon, when we operate the station, we need multiple systems and facilities, so that are also required, included in the Artemis project. In the original plan, we were supposed to finish Artemis project phase 1 by 2024. However, there has been some delays. So on the surface of the moon, there will be lunar lander. So I will explain this. So we call this as CLIPS, which stands for Commercial Lunar Payload Service. In the era of new space, now private sector will develop the lunar landers, unlike the past when the public sector developed the lunar landers. On the left side, you can see SpaceX, Blue Origin, and many other developers have been registered as a lunar lander developer. And for 3 years, I believe you need to pay attention to this. The public sector is now respecting the philosophy of the developers. In the past, the public sector made the requirement and the developers had to follow the requirement, but now the philosophy of the developer is respected and lunar landers have been developed. So let me explain what is the Korea-US Private Lunar Lander project. So this project is a collaborative project led by Korea Astronomy and Space Science Institute. So the scientific payload will be developed in collaboration with NASA and Korea Astronomy and Space Science Institute. And in total, 4 scientific payloads will be developed. And the first one will be loaded and launched in 2024, and 3 other scientific payloads will be launched after 2025. This is the structure of the project. At the bottom, you can see 3 organizations are working together. So there is Korea Astronomy and Science Space Science Institute, SATRIC-I, and Gyeonggi University. And at NASA, the lander is developed by an organization called Intuitive. And Space Science Laboratory and Johns Hopkins University are also working together. And we call LUSEM the Lunar Space Environmental Monitor. And the discussion started in 2020. And as of November 2022, the flight model has been completed. Let me explain this briefly. We would like to monitor the radiation environment on the surface of the moon. Unlike the Earth, there is no atmosphere or global magnetic field, so there is no shielding effect. So, the solar wind and high energy particles will be radiated directly to the moon. So there are multiple physical and chemical effects on the surface of the moon. So we call this as a space weathering. NASA created this promotional video for the Artemis project. In order to promote CLIPS, they created this YouTube video. So when you look at this video, you can see what kind of development will be included in this project.
The solar wind is the sun's continuous outflow of particles and radiation that fills the inner solar system.
From the sun, the radiation particles will be generated, and on the Earth, there is radiation radiation shielding effect due to the global magnetic field. However, in the moon, there is no magnetic shield, so there are multiple effects. And local magnetic field can be observed on some areas of the moon,
are locally acting as this magnetic sunspot.
and we can also observe the lunar swirl as well.
And then you have a really bright red
We
spot on your skin where you
assume
miss it.
that
That's in some
these
ways the analogy of this
things
sort of
can be
region
observed
of
on the
that's extra
moon.
exposed.
So what he is saying is, when we apply sunblock on our skin, we can block the sun so that we can avoid burning. Just like that, on the surface of the moon, we can also avoid the space weathering on the surface of the moon. The cosmetic magnetic field can create the radiation, and there are multiple theories about the cause of the space weathering, and the critical evidence is the regolith obtained by Apollo, and there are multiple potentials. Usually we say that due to the radiation field, a solar field can be shielded, and there are magnetic anomaly or a lunar swirl can be observed. On the left side, you can see the linear gamma, which is the representative lunar swirl. What you need to look at is the black area, and this is a stone. And unlike the black area, you can find the white area. This is anomaly. And in order to understand this, scientists analyze this, and we assume that there is a strong magnetic field, and due to this magnetic field, solar wind is shielded. In order to understand the magnetic anomaly, we will launch the launch vehicle. And I introduced the surface of the moon, but aside from the moon, there are multiple planets such as Mercury, Europa. So inside the solar system, there are so many objects, so we can apply the knowledge we obtained on the moon surface. So we believe that this project can give a clue for other projects. And this is the structure of the LUCEM. And there are two main parts. On the left side, you can see the detector, and on the right side, you can see the front side. So high energy wind, solar wind particles will be detected, and there are electronic parts, so this will analyze the particle and send the information to the Earth. And this is the LUCEM, and this is the picture of the certified model. And on the right side, you can see the sensor head. Just like the bottom of this slide, you can see the structure of the sensor. And on the right side, you can see that the equipment is wrapped in orange. In order to avoid the scratch on the surface of the moon, we used a multi-layer blanket. This is a little bit technical, but as for the LUCEM, we use the PN junction diode called solid-state detector, and we use the magnetic field and foil to distinguish the electron and proton. And on the left side, you can see the schematic drawing, and in the OSEM area, we can sort out the electron, and 350 cannon can be filtered, and we use this electron filter. And as for a proton, it is heavier than electron, So when we use the membrane, we can also filter out the electron and proton. So we use the foil to filter out the heavy proton. This is very busy slide, but this is the overall diagram. And let me introduce the electronic devices. On the top right corner, you can see the final result, and it is exposed to the outer space. So we used the outer layer as well, and you can also see the processor, and you can also see the electronic parts without the layer, outer layer. And we already finished the environment test, and flight model has been assembled. As for the environment test, we started the test from September last year to May this year. From unit level test, the integrated test, thermal cycle test, conformal coating and biversion test, and EMC test. So without any problem, we finished all the tests and confirmed that the development has finished successfully. And we carried out this test in Gyeonggi University. The purpose of the test is to see whether they have enough performance. On the left bottom, you can see all the different parts, and we proved that the detector is working well. And on the right side, you can see the color-coded graph, and ion and electron have been detected under the less than 50 kV. So we proved that they have the strong enough performance. We used actual radiation to confirm the performance of this device, and in the vacuum environment, we used multiple radiation to see the device we developed can show the performance. So we demonstrated the performance of the device, and americium 241, barium 133, and cesium 137. And as for the energy, we used 37 keV to more than 600 keV. And this is the calibration curve. On the right side, you can see the linear line, and this is the relation between energy and channel. The angle of the gain is relatively low for the F, because this is intentional because we wanted to see the outcome for other research purposes as well. And we successfully completed the environment test as well. Traditionally, there is a thermal vacuum test and EMC test. And when you look at the outcome, first, as for the vibration test, there was a vibration at 4,000. And we carried out this shock and vibration test in a certified test lab. And we also carried out the thermal vacuum test at KAIST. Last but not least, as for the EMI-EMC test, we conducted the test in a certified test lab in Osong. the lunar lander we developed, the LUSAM we developed will be mounted on the lunar lander, and the outcome of this LUSAM and the lunar lander can be seen on the right side. So on the left side, you can see the electronic parts, and on the right side, you can see that the view of the detector is not interfered by other objects. From the US, they selected an organization, Intuitive Machine, and they sent this data to Kyunghee University. So you can see LUSAM is mounted on top of the lunar lander. It is mounted on the side and top part of the lunar lander. When we send the lunar lander to the moon, there is a sensor header, so you can see how it will be mounted on top of the lunar lander, and we secure the field of view, and sensor is looking at the top part and the downward, and the electronic parts are also located on top of the lunar lander. And we have this scenario for the operation of LUSAM, and NASA and Intuitive Machines also agreed with this scenario. So we wanted to have this simple structure, and there is a high possibility that it goes through the radiation field. So we need to turn on this device and to receive and detect as much as possible. So we will turn on the device early on, and if there is no other problem, we will continue the detection. And this is the future plan. As of November 2022, we are making the flight model and functional test. We were supposed to finish this functional test earlier. However, now we are waiting for the outcome of the functional test, and in the first quarter of 2023, the environment test for a flight model will be completed. And we will hand over the flight model to the US, and once it is handed over, Intuitive Machines will mount this on top of the lunar lander, and once we finish everything successfully, in the third quarter of 2024, the lunar lander will be launched, and as I said, this will be landed on the liner Gamma, and important information will be gathered through this device. Thank you very much. Professor Sun, thank you very much for the presentation. If you have any question, please raise your hand. Then let me ask a question. Up until now, as for the space environment monitoring, we use the geostationary satellite or Lagrange point. But when we land on the moon, is it possible that we can monitor it? In the past, Apollo was used as a monitoring station, and even though I didn't provide a detailed explanation on the surface of the moon, we have a main purpose of this project. So the purpose is providing the information, but in Apollo 13, they observed the moon, and we can observe what happens when the Earth is located in the tail of the moon. So aside from Lucene, in applied physics level, they are creating another device for low energy area. So we will analyze the data in connection with the data gathered by applied physics. So I believe we can make an observation on the surface of the moon. If there is no other question, we would like to finish this presentation here. Please give a big round of applause.
네, 다음 발표는 이제 후속 기상위성 이제 GK5에 탑재될 우주환경 탑재체에
The next presentation is on the next generation space weather payload for the GK5, and the presenter is Mr. Nam Woo-kwon from Korea Astronomy and Space Science. Hello everyone, I'm Nam Woo-kwon from Korea Astronomy and Space Science Institute. There are some projects that are related to the GK5, and I'd like to share with you what's happening with those projects. This presentation was put together with Mr. Kim Ji-yoon from the Satellite Wave Monitoring Center. If you look at the space weather related rule of KMA, weather satellite and polar route aviation meteorology and ionospheric weather are some of the main tasks. So far, a lot of focus has been made on the weather satellite related tasks. From KMA, they have their own geosatellite, geostationary satellite. So they want to develop various weather-related payloads in order to generate many space weather-related data sets. And based on such data, they can establish plans to protect critical assets vis-a-vis the space weather conditions. So KSEM package is now in operation, and I'd like to talk about the necessity of the development of KSEM2. You know already that we rely on GOES data, and the situation is same in Japan. But the space environment above the Korean Peninsula and above other countries may be different. So in order to protect our critical assets, we have to have independent monitoring. We have KSEM monitoring system on COMSAT 2A, but we want to ensure continuation of our task, and we also need to strengthen the Korea weather forecasting. If you look at the local community, there is a next generation space environment related projects, and in Korean Air Force, so they want to protect their highly advanced space weaponry, and they are now conducting projects to improve their forecasting capabilities. And there are also Korean navigation related projects. So if you look at the domestic community, there is a lot of interest in space weather data. From the space weather point of view, you all understand that there is a gradation belt and inner belt, and the geostationary satellites are located in inner belts, and there is a long-term electron dose effect that we need to think about. And we also need to look at the surface and directly charging regions. Within the radiation area, there is intense protons and other heavy materials that also impact the satellite operation. So For GK5, which will be on the geostationary orbit, these are some of the things that we need to monitor, and that's why we need the new KSCM2. And there are a number of space weather-related parameters, and there are different energy bands that we need to monitor. And there are also various effects that we need to look at, and we cannot have one monitor to cover these all parameters, so we need to have different instruments. When it comes to the operation of the satellite, there is surface charge or internal charge related electrostatic discharge that can be highly influenced. And as you see, internal charging can have significant impact, and there's also single event offset and others that can cause some influence. So in order to have monitoring of these, we have to have new instruments. So from the point of the space radiation spectrum, electron is 0.2 to 4 MeV, and proton measurement should take place from 1 to 500 MeV. And within this scope, there are trapped electrons, protons, and solar storm protons, and the KSM does not cover the entire electron and proton area. We only have partial coverage. That's why we need the new KSEM to be able to cover the entire area of interest. If you look at the ionosphere weather conditions, I think the Korea Space Weather Center is also interested in this area. If you look at the ionosphere, there is a dragging effect caused by the lower orbit satellites because of the expansion of the Earth atmosphere, caused by the increase of the electron density, and it can have impact on the ionospheric layers D to F and can impact the satellite communications. And there is only a 5 to 10 minute time frame that we don't have any impacts, but it can also cause impacts on the layer F. And if we can have domestic capabilities, we can reduce our dependence on ghost satellites, and we hope to develop our domestic systems to be able to have independent monitoring. Now I'd like to talk about what's happening in other countries. Since I have limited time, I'll skip some of the slides. So GOES is the US satellite, and there is the East operation and the West operation. And when it comes to the space weather, a lot of times we rely on the GOES data. And there are a number of countries that are reliant on the GOES data. And if you look at some of the instruments, we are interested in Space Environment Institute and Extreme Ultraviolet and X-ray Irradiance Sensor, which is EXIS. Probably I'll be able to provide more explanation, but as you know, the Space Environment Institute suite has 4 different sensors to monitor different elements like the protons, electrons, and the neutron flux. Moving to China, they have a large scale instrument, and they also upgrade their satellites every 5 years. And so they are quite active. If you look at these instruments, there are a number of sensors, and they're comparable to GOES actually. They have what's called the XEUVI, and this is a package of devices, and this is used to monitor the space weather. And this has a compact design. Maybe we can benchmark the configuration of this instrument. And it is in operation and is being used for monitoring, and the Chinese authority continues to upgrade this instrument. For ESA,
위성체 하우스키핑 개념으로 들어가 있기 때문에
They're more focused on satellite housekeeping.
좀 간단한 시스템이 들어가
So they
있습니다.
have rather simple system. They have electron, proton, and heavy ion monitoring system, which is made as a package. They improve their systems, but we haven't seen any dramatic improvement, but they are doing some performance improvements. But they still continue to upgrade their systems, and now they are trying to obtain data to be used for space weather forecasting. And this is the instrument that Japan is using. This was used for the housekeeping purpose, but as they plan for the next generation Himawari, they are now upgrading their system so that the data can be used for space weather forecasting. So this instrument is quite similar with the system of ESA, but compared to GOES data, the outcome is, or the level of the outcome is only 50 to 80% of the GOES data. So there are a lot of things that the Japanese authority is struggling to improve. And as you see on this slide, there is a development of the development of the timeline, and they are trying to obtain data that could be used for the space weather forecasting. Compared to GOES data, Japan and ESA has high energy electron proton measurement that they are focused on, and China covers the most energy band. And for GK2, it's a first generation space weather packaging, and the charging monitoring is electron and lower energy proton, and that is the measurement capability. Now I'd like to briefly talk about the sensors, and there is a charging monitor. And this measures the integral fluxes of the charged particles, and there is an internal charging monitoring device inside. And in Japan, they benchmark the Korean system. They say they have the surface and internal monitoring capabilities that they want to pursue going forward. If you look at the GOES MPS high, the electron measurement is from the 50 keV to 4 MeV, and they measure protons from 80 keV to 10 MeV, and this is related to internal charging. So this energy band is really important. Moving to Japan, they have the stacks of aluminum plates. If you look at the measurement or monitoring data, compared to GOES, it's only as high as 80%. So they want to upgrade their system in order to obtain quality data. Now, talking about the proton sensor, the measurement can take place for 1 MeV to 500 MeV energy range. And this is used for solar S index. We are hoping that the next generation KSEM-2 can be able to cover the same energy scope. There are two silicon coincidence logic that's used for this center. I don't think the performance is very good. There is also a dosimeter, and the dosimeter is related to the satellite component's life. And there is also a heavy ion sensor. And in GOES, there is their own unique instrument, but here it is related to single offset event data for Europe. This is not highly precise, but China and Europe are monitoring the heavy ions for the same purpose. And GOES data is used as a basis. And as you see, this was set up for solar setup. And this is the GOES X-ray sensor structure. And flare temperature and flare location and flare strength can be measured. This is the Chinese sensors. There is an X-ray sensor and EUVA sensor put together in one device, and that is in operation. And considering X-rays, if you look at the current trend, there is a next generation X-rays. If you look at the GOES data, and they're using their 15-year-old instrument, and they only monitor the flex of the solar flare, but now they want to measure the higher energy spectrum. There is Chandrayaan lunar orbiter that has the US equipment, and there is also CubeSat that also has the European device. And there is next generation X-ray monitor in the Chandrayaan, and there is also a comparison with the payload mounted on a satellite. And the yellow one is the GOES data, and the blue one is the Indian measurement, solar flux monitoring outcomes. And it is better than GOES. So you see the measurement that cannot be obtained from GOES. And I'd like to talk about what's happening in Korea. And as was mentioned, KSM is now on GK2A, and it is in operation. And Kyung University developed KSM, and the data is obtained, or is being obtained. This is an internal charging monitoring, and this is an example of the monitoring outcome. Electron and charging monitors have a good coincidence, and we are obtaining quality data. And if you look at the particle detector, this is the structure of the particle detector, and we are obtaining data from this particle detector.
그다음에 이제 관련된 파티클 디텍터 쪽은 천문연에서 지금 스나이퍼 편대 비행
There is a snipe formation
아직 발사는 안 됐지만
flight, and this is not launched yet, but it will be launched, and we already developed relevant technologies, and this will be developed for Eclipse, and proton measurement from 1 MeV to 500 MeV will be possible, and this has a really compact design, and heavy ion and dosimeter can be monitored. This will be launched next year, and this will be used to monitor the space radiation on low Earth orbit. And I hope the Korea Space Weather Center will think about utilizing the data that we'll be able to obtain from this dosimeter. Silicon sensors are used to monitor X-rays, electrons, and protons, and it was developed by Gyeongbuk University, and it can be used for the next generation KSAM. Speaking of the EUV sensor, along with the X-ray sensors, EUV sensors are something that a lot of Korean scientists are interested in. For geostationary satellites, EUV sensors must be developed to be used. Of course, we can use the GOES X-ray data, and some say that why we want to develop the same sensors on our own to get the same data.
좀 뭔가 차별화를 하려면
We need to be differentiated, and we should be able to monitor both X-rays and EUVs. And if you look at if you look at the local community's interests, they are also highly interested in the EUVs. So it is critical for us to develop the related technology so they will be able to develop our own EUV sensors.
이제 우리가 XEUV 단점이라면
But there are some disadvantages. It has to have a sun orientation, so we also have to develop our own gimbal system. This is 20 kilograms in weight, and more than 4 billion Korean won will be required to develop the gimbals. So we have some financial burdens to be able to develop this to be used for our next generation GK5. But I think it is still necessary. With only one system, we cannot cover 100% that we want to measure. According to our simulations, we can have at least 80% to 90% in performance. But if we use two systems, of course, we will be able to have 100% of performance, but we of course have some weight limitations. For the GK5, magnetometer developed by ESA will be used as an interface, and it was the case with GK2 and it will be the case for GK5. But in Korea, there are some projects that are going on in order to develop our own technology. So for next generation, hopefully we want to have domestically developed magnetometers. And this is a critical technology that is related to the magnetometer. And we have the electronic units, and there is a technology owned by and developed by the Korea Astronomy and Space Science Institute. So I looked at some of the trends that are happening in Korea and other countries, and I also shared with you some of the important instruments. And there are 5 different categories, and category 1 is related to the satellite operation, and our target is to have proton measurement from 1 to 500 MeV, and we want to obtain data that will be used for space weather forecasts. And it can be also used for the polar route and space weather. When it comes to electron, this is also related to obtaining data related to space or satellite operation. There is also charging motors and magnetometers that we will want to develop and secure. So far we've categorized the instruments that will be required, and we will select the candidates to be used for GK5. So I already explained to you why we need to develop these, and now we need to have discussions on what sensors will be developed. We already have the priorities determined. When it comes to the X-ray, there is some consensus about the necessity of having new X-ray sensors. But of course, we have limitations of budget, and if you want to have all these sensors, it is quite heavy. So that's why we need consultation with the GK5 developers, and we need to think about the trade-off between the technological requirement and budget. For X-ray and EUV of the ionosphere, if there is a strong appeal from those who want to develop these sensors, you have to make your strong case. Through planning, we will continue to have our conversations to select the sensors but still we haven't initiated the feasibility study, and there may be some changes during the budgeting process and the feasibility study process. Every 10 years, we develop our new technologies, and we will continue our domestic R&D efforts in order to maintain our technological capabilities. And we need to improve our infrastructure to be able to further sophisticate our technological advancement. And there are some extra efforts that will be required in that regard. What we want as a community is to select the proper sensors so that we'll be able to improve our data generation capabilities and develop sensor technologies for space weather forecasts so that we can all generate good research outcomes. With that, I will conclude my presentation. Thank you very much for your attention. Thank you very much, Dr. Nam. If you have a question, please raise your hand. I'd like to ask you a question. You shared with us a list of sensor candidates. So do you have any internal priorities that you have in mind? So is there any candidates that you believe strongly in? Sorry, I was not able to hear you clearly. Can you please repeat your question? Can you please go back one slide? So this is a list of sensor candidates. And your question was? So you have these 8 sensors. So are you planning to include all these 8 sensors? As was discussed in my conclusion part, if you want to include all the sensors, it's going to be too heavy. So there is also a trade-off. Last year, when we were preparing for the budget feasibility, the limitations was 40 kilograms in weight and 40 kilowatts in power. If we want to include all the sensors, we'll have to overcome the weight and power limitations. But we created this list, and these sensors are critical. You want to have in place a good level of space weather capabilities. But we need to, of course, have priorities. And if we select a number of sensors, they will, of course, go with the GK5. And if some of the sensors are not included for GK5, those will be included in the next generation satellite. So as for the time being, I don't believe that we'll be able to include all 8 sensors in GK5. Any other questions from the floor? I think I asked this question already in another occasion, but when I looked at the Jimbo graph, there is no monitoring at noon. And you shared the simulation result. I think it's better that we don't have the monitoring capabilities at midnight. Is there any solution that we can have the monitoring capabilities at noon? So, to answer your question, if we have the systems at the best location, because the satellite is tilted by 23.5 degrees, there is some shielding, and we have to have a high setup
하여튼 베스트 포지션에서 얻을 수 있는
And we have to
게
have the best positions of the satellite.
80%였고요.
And the outcome was the 80% that we obtained from the best position. At around noon, there was no monitoring. And if we adjust the position of the satellite, that issue can be resolved.
데모스트레이션 차원에서 이런 방향에서 이렇게 셋업하면
And we only demonstrated the duty that we could obtain at the particular positioning. And if we have the final location,
잘 시뮬레이션 해가지고
we will do a simulation
우리
so that
관측에 지장이 없도록
it does not cause any trouble
근데 이제 여전히
for our monitoring.
우리가 전파연 쪽에서 얘기하는 거니까 우리가 그 고저 대비
Compared to GOES, if we want to achieve 100% performance, we will face a lot of challenges.
좀 의미 있는 관측이 그래도 결과가 나온다면
And if we can
그렇다면은 그
obtain only 50% of the data compared to GOES, we'll be able to enjoy more leeway in selecting our sensors. And the Chinese field of view is only 40 degrees. Maybe they will forego the Jimbo system. Of course, we will need a further analysis on that. We don't have any instruments discussed and finalized yet. But what I can say is that for our own space weather forecasting, there should be a strong appeal from the organizations that require data. That will really help us with the selection of the sensors and instruments. So please make a strong case as a community. And in that regard, I need your support. So within the domestic community, that's the action that that's required. So it all boils down to how we want to play with the limitations of weight and budget. And taking this opportunity, I'd like to say a few other things. It doesn't have to be the geostationary satellite. In order to obtain some preliminary data, the domestic CubeSats and heavier satellite programs can be used to select and make a case for the new instrument. I hope that there is a more active engagement from the National Radio Research Agency. Maybe we will be able to add new sensors with not GK5 but probably GK6. Since we are running out of time, we will have to move on to the next presentation. And Dr. Nam, thank you very much for your presentation.
Let us move on to the next presentation from Professor Lee Dong-hoon of Kyunghee University. He will talk about the space weather in the era of new space. Good morning. This is the 12th Space Weather Conference, and thank you very much for the opportunity. I'm very happy to be here. And the title of my presentation is not familiar to the general public. So we are talking about space weather, and we are talking about various conditions. So in the new space age, how it should change, what kind of preparation is required for us. I'd like to talk about this in my presentation. And as you may know very well, the new space age has started from 5 years ago. And one of the most representative characteristics is in the past, the public sector spent lots of money and invested a lot of money to develop the space. However, the main player is now the private sector. The companies are making investment to create lots of profits. This kind of trend can be seen all around the world, and qualitatively and quantitatively, we can see a large change in the space ecosystem. So new space age means that. And one of the good examples of the new space age is, as you can see in the slide, hyperconnectivity in space. So we can emphasize the hyperconnectivity all around the world. Recently, with the development of information technology, we can see the fourth industrial revolution, and using AI and big data, there is a development in fourth industrial revolution. And in our daily life, we use mobile technology, and space is also connected with high speed, so we can respond quickly. We can activate something very quickly. So hyperconnectivity is one of the characteristics of the fourth industrial revolution era. And in this sense, we need to look at the changes happening in the space, and it is covered frequently in the media. The entrepreneur Elon Musk is leading SpaceX project. In the past, he focused on the electronic vehicles, but nowadays, Elon Musk is mentioned frequently in the space area. And there are two things in regards to SpaceX we can see frequently. The first one is a launch vehicle. Large-scale launch vehicle can be created with a small amount of money compared to the past. And large-scale government programs also use the launch vehicle created by private sector. And another one is Starlink. So a large number of satellites are launched to the space, and Elon Musk is one of the leaders. So on the background of this slide, you can see many dots and lines connecting the dots, and these dots represent the satellites. So on the low Earth orbit, or LEO, in the LEO, many satellites have been launched, and they provide communications services to use it for the economic activities. In the past, of course, the satellite communications had been available, and we've been using it for decades, and we can use it for the broadcasting of sport games. But in LEO, usually in the past, we used the geostationary satellites. They are about 1,000 altitudes from the ground. However, the LEO is much lower. So using the low Earth orbit satellites, Elon Musk is trying to enable the internet and communications technology. So this new trend is emerging. Aside from Starlink, there is also Kuiper project from Amazon. And there is also another one called OneWeb satellite network. And aside from these networks, there are various types of satellites, and they are creating a network to use as a communication technology. In recent 5 to 10 years, this trend is emerging, and this is a rapid change. And China is also implementing the similar project. The number of the satellite is increasing, but we can not understand how many. So we need to understand how many satellites are on the air. On the right side, you can see the data as of this spring, this year. These are the satellites in the air. But when we exclude the non-operating satellites, there are more than 5,000. And by country, the US has the largest number of satellites in the air. And as for the LEO, it is a low Earth orbit, so the altitude is low. And as for GEO, that means the geostationary orbit, and MEO is a medium Earth orbit. And the number of the satellites on LEO is more than 4,700, so it is more than 85%. This is the recent trend, and 20 years ago, 30 years ago, when we look at the statistics, there were just around 1,000 LEO satellites, and GEO satellites were 450, and MEO satellites were about 500. So the ratio between the geostationary satellite and LEO satellites were half and half. However, nowadays, the number of the GEO satellites are 500, but the number of the LEO satellites has increased by 10 times. I believe you have seen the news articles, and there are limited number of available spots for satellites, and we are competing for the satellite spots. As for the GEO, we cannot increase the number of the satellites on the geostationary orbit because there are limited spots. But as for the LEO, the number of the satellites has increased. And within 10 years, the number of the LEO satellites will increase to several tens of thousands of satellites. We can compare this number of the satellites with the number of the flights. Due to the COVID-19, nowadays we can see the reduced number of the flights on the air because less people are traveling around the world. However, when we look at the data of 2019, before the COVID-19, all around the world, in a day, per day, around 180,000 flights were on the air. Of course, there are ups and downs depending on the days, but this is the average number all around the world. However, as for the satellites, they're always in the air. So we need to compare with the number of the flights in the air at certain point. So as for the mid-flight planes, 8,000 to 20,000 flights are in the air at a certain point. Maybe during the nighttime there will be less flights, and during the daytime there will be more flights in the air. According to our observation, if the number of the flights increase to 10,000 or 50,000, there will be more satellites than the flights in the air. And they are staying in the air.
이동, 트랜스컨티넨탈
So-
대륙을 가로질러 가는 그런 멀리 가는 그런 플라이트들을 보면
When we look at the transcontinental or
적을 거라고 했지만 이거는
long
하루에
range
8,000개에서 2만
flights,
사실은 이거의 10분의 1도 안 되죠.
the number of the
1,000개가
flights
안 돼요.
is
국내선이
10,000.
대부분이지 뭐
Sorry,
멀리 가는 것도
1,000.
얼마 안 돼요. 그래서 사실상 굉장히 장거리로 해서 가는 비행편보다는
So compared to the long range
이
flights,
위성 수가 훨씬 더 많아진다는
the number of
얘기입니다.
the satellites will be much bigger.
이런 그 에리오 지역에 있는
In
그
the
위성들
low
다수
Earth
위성,
orbit,
망,
there are so many satellites, and they are creating the satellite constellations.
이제 이런 위성망에서 우리가
In this satellite constellation,
정말 많아져 갖고 나중에
in the low Earth orbit,
이렇게 하면 뭐
if
5만 개 전 세계적으로 이렇게 된다고
there
치면 지금
are
나와 있는
more
계획만
than
보더라도
50,000
이제까지 올렸던
satellites,
모든 위성들, 뭐 발사했던 모든 위성들 그리고
all the
비행기
satellites
합친 것보다
we've
훨씬 더
been
숫자가
launching
커지는데
will be
이렇게 그
bigger
빠른
than
변화가
the
일어나고
flights
있는데
in
이제
the
그
air.
위성망
So we
올린
can
게 5년
see
정도밖에 안 되거든요.
rapid changes.
그런데 우리가 기존에 하고
And
있던
we've been
스페이스
launching these
그런
satellites
서비스
frequently
가지고 이런
for
급격히
the last
변화하고
5
있는
years.
신우주 시대에
In
이런
this new space age,
활동들을 우주에서 활동들을 충분히 이가 예경보 서비스를 할 수 있느냐 이런 좀
we are very active
질문을
in
가지지
space
않을 수가
operation.
있겠죠.
So
그래서
the question is whether we can provide
저궤도 위성 수가
timely
폭증하고 있는데
warning
이걸
and
어떻게
prediction
실시간으로
for space weather.
우리가 이 지상에서
The number of
지상의
the
그 날씨
satellites
예경보하듯이
on
실시간으로
low
이런 정보들을 좀 제공하는
orbit
그런
is
스페이스 웨더
exploding.
서비스를 해야 되지 않나.
So I
이런
believe we
수요가
need to
이렇게
provide
수요가
excellent
요구된다고 할 수가
warning,
있겠습니다.
and there is obvious demand for
그
that.
에리오 위성들을 활용한 이런 뭐 우주 통신
When we use the LEO satellites,
발전 가능성 이런 것들을 보면
communications
최근에 이제 뭐 아까
would be
말씀드린
possible.
그 스타링크를
As I mentioned before, Starlink will be formed,
러시아랑 우크라이나
and unfortunately, the war is ongoing between Russia and Ukraine. In the initial phase,
뭐 이런
in order to cut down communications, Russia cut down the internet lines
그래서
to disable the internet and communications.
정보를 다 차단시키고 서로 통신을 못하게 막았는데
So Russia blocked communications between Ukraine and many other countries, but it was addressed very easily. Starlink is now doing the beta service.
우크라이나에다가 여기 피자판만한 그런
So in Ukraine,
위성 안테나와
if they have the
쓸 수 있는 우리 보통
antenna
휴대폰 생긴
as big as
던져주고 그럼 거기다 이제 파워만
a
꽂아가지고
pizza,
하면 뭐
and
아무나
if
다 통신할 수
the
있게
antenna is connected to the power, anyone can use the Starlink provided internet
아주
service.
쉽게 그냥 막을 수가 있었어요.
So this connection of the internet can be addressed very easily. In the past, we used wired communication. One of the representative wired service is optical internet.
대륙 간의 이런 도시들
And among
그리고 인구들이 많은
continents,
지역
cities are connected together, and there are fiber optics cables connecting all the cities and populated areas. However, in the ocean and in the Arctic area, it is not connected, so there is a huge gap depending on the region. And when we cut those lines, some areas will be isolated and internet service would not be possible. We need to overcome the regionality of the internet, and one of the ways is the space internet. From the space, the internet service can be provided everywhere, whether you are in the desert or in the ocean. And the space internet has another differentiation in technology.
예를
which
들어서
is the speed of the
우리가
internet.
어떤 뭐 정보 시스템을 인터넷으로 이렇게 연결해 놓으면
When we connect a
한
system
지역
with the
대륙에서 다른
internet
대륙으로 가는데
from
가장
one
빠른
continent
것이
to the
이제
another
옵티컬
continent,
파이버로 해서 연결해
the
가지고
fastest connection is
잘
optical
아시는
fiber.
대로 그 옵티컬 파이버에서
As
가면
you know, when we
불전율이
go
있기
through
때문에
the
빛의
optical
속도로 가는 게
fiber,
아니라
there is the deflection,
불전율이 1.44 뭐 이렇게
and
되죠. 그래서
deflection rate is
1.44분의 1이 되기 때문에
1.44.
한 69% 정도
So,
빛의 속도의 한 70%가 거의 70%
around
정도로 줄어듭니다.
70% of the light speed will be
대륙을
decreased.
건너갈 때는
So between
제일 빨리 가는 게
continents,
빛의 속도의 70%로 가는 게 제일
the
빨리 가는
fastest
거죠. 그것도
internet
일직선으로
speed,
간다고 했을 때.
communication speed, would
이제
be the
위성에서
70% of
보면은
the light speed. But when we
위성은
use
이제
the
이렇게 위로
satellites,
여기 그 파란 오른쪽 위에 그림에
as you
보시면
can see on the
녹색선을
picture on
따라서
the right
통신을 하게
side,
되고
the
지상에서 한다면
communication
지구
will be
표면에 따라서
done
보니까 이제 빨간 선을
on the green
지구 표면에 따라서 가게
line,
되는데
and on the
물론
ground,
고도에
the
따라서 위성이
communication will be
높으면
done
지상에서
following
위성까지
the
올라가는데
red
더 이렇게 많이
line.
돌아가니까 이 거리 그 이동 거리는 더 되지만 그
Even though
전체 이동
the
거리가
total distance of the
70%
communication will be longer compared to the
정도
ground communication,
줄어들어도 지상보다 더
however,
짧으면 더 빠른 시간에 갈 수 있으면 더 빨라질 수가
if
있어요.
we use
이게
the satellite
멀어지면
communication,
멀어질수록
it will be
그런
faster
효과들이 더
than
많이
the ground
나타나겠죠.
communication,
왜냐하면
and it will be
위성과
more
지상
effective
간에 걸리는
when
시간은
the
정해져
distance
있기
between
때문에.
the 2 points will be
그래서 이제
farther.
위성이 이런 식으로 계산을 하면 위성이 아래 오른쪽 아래
So
그림
when
보면 이제
we
까만 부분은
calculate this, the outcome
위성을
can be
통해서 하는 게
seen
더
on
빠른
the
거고
right side graph.
저기 회색으로 된 거의
The
윗부분은
gray area
옵티컬
shows
파이버를 하는
that
속도가 더 빠른 겁니다. 그래서 보면
satellite communication is faster than the
X축이
optical fiber
이제
communication,
이
and on the white
지상에서
area,
떨어지는 게
the
거리가
optical
얼마큼
fiber
되냐. 오른쪽으로
communication
갈수록
is
멀면 멀수록
faster than
뭐
the satellite
그래서
communication.
뭐 뉴욕이랑 서울이랑
For example, between
또는
New
뭐
York and Seoul,
LA랑 뭐
or
런던이다.
between
이렇게
LA
해서 점점
and London,
멀어지면은
if the distance is
위성을 통하는
far,
속도가 더 빨라지는 겁니다.
then
멀기 때문에.
satellite
이
communication will be
고도가
faster than the optical
2,000km가
fiber
넘어버리면
communication.
위성의 고도가 2,000km가
If
넘어버리면
the satellite
어떻게
altitude
해서도 하는
is
것보다 지상에서 하는 게
higher
더
than
빠릅니다.
2000,
올라가고 하는데 시간이
then
다 걸려버리기
ground
때문에
communication will be
그래서
faster
정지궤도는 뭐 당연히
because
뭐
there is a
몇 초씩 이렇게
delay
잡아놓고
between the
고도가
communication
2,000km 이상
in the
LEO를
communication
넘는
between the
그런
ground
위성이
to
돼버리면
satellite.
시간적으로 더 빨리 할 수 있는 통신할 수 있는 방법이 없는 거죠. 그래서 LEO에서 고도를 낮추는
So
거는 그런 통신
we need to
속도를 빠르게
use
하는
the
게 굉장히
LEO,
중요하다는
the low
것을 알
Earth
수가 있어요.
orbit, and low
근데
Earth
우리가 뭐
orbit is
속도가
very
빨라서 뭐 이렇게
critical in
중요하냐라고 할 수
using
있지만
the high-speed
이게 무슨 뭐 한
communication technology.
지역에서 증시가
You
마감되는데
may wonder
그 증시가
why this
마감된 그런
high speed
숫자가
is
다른
important.
대륙에
For example,
가장 빨리
the
전달돼갖고
stock
뭐
exchange
자동으로
market
처리해서 그 숫자를
will
기반으로 해서
close
또
at
이렇게
certain point,
뭐 구매한다든지 이렇게 할
and
때
based
제일
on
빨리
the
되는
closing number
한다면
of the
경제적으로도
stock
엄청난
exchange,
임팩트가 있겠죠.
there might be other
이런 뭐 이런
transactions.
증권 회사들이나
So
이런 데도
this
이
high
옵티컬
speed
파이버를 새로 깔아고 속도가 빨라지고 성능이 좋아지면
is
다
hugely
굉장히
influential
많은
to
거액을
the
들여가지고
economy. That's why
그
many
서비스를 채택하고 지금 그런 와중인데
stock companies
근본적으로
are
이런 속도가
using
다른
the
우주
high-speed
인터넷은 경우에
optical fiber.
그런
But when
특징이
we
있습니다.
use the
근데 이제
satellite
불행히도 그
internet,
LEO
it
위성들이
will
이렇게 많아지면
revolutionarily change
우리가 지금 관심 있어
the
하는 그런
speed
스페이스
of the
웨더에
internet.
의한
And
영향들을 많이 받지 않겠냐 이런 걱정이
the
앞서고
concern
물론
is this
지금까지는
satellite internet
그렇게
can be
많은
affected
수의
by
위성이 올라가 있지
space
않았기
weather.
때문에
Of course,
우리가
at the
뭐 우주
moment,
탐사
we don't have
위성이나 이런데
a
뭐
large
신호가
number of
절대
the
안 들어와도
satellites,
되잖아요.
so
몇 초 있다 다 받으면 크게 지장이 없는데
only several
그게 이제
seconds of this
실시간 그
disruption
경제 활동에 활용되고 있거나 그러면 조금이라도 장애가
can
생기면
be
큰 문제가
endured.
생기겠죠.
However, when we
그래서
use
그런
this technology for the daily
측면에서
lives,
보면은
several
우리가
seconds of
스페이스
the
웨더의
disturbance
효과를
can
이제 더 이상 간과할 수
be very important.
없다라는
So
것을
we cannot
알 수가
ignore
있어요.
the importance of the space
그
weather
금년
anymore.
2월달에 이제
February this
스타링크가
year,
막 위성을 계속 올리고 있는데 이게
when
41개짜리를 올라가
Starlink
40개를
launched more
분실했습니다.
satellites,
올라가다가 이제
they
스페이스
actually
웨더에
lost 40
영향을
satellites
받아가지고
due to the space
궤도에
weather
오르지
disturbance.
못하고 이제
So they failed to
그런
reach the orbit.
더 고도가 낮게 됐기 때문에 다 잃어버리고 스페이스
The
웨더에
satellites
직접
failed to reach the
그런 장애
orbit and
현상을 우리가
lost
목격하고 있습니다.
40 satellites.
우리 이미 2003년에 이런
In 2003,
이런 여러 가지 장애 현상을 이미 확인한 적이
we
있고,
already
그래서 전 세계적으로도
witnessed
보고가 잘 돼 있었고,
several disturbances.
어저께도 뭐 전리권 부분 또
And
지사기
yesterday
부분에
there was a
어떤 것들이
presentation
나타났냐는
regarding
사례들을
the
구체적으로 들을 수
ionosphere
위성만
disturbance
보면
and
2003년에
geomagnetic field
어떤
related
장애 현상을
disturbance.
겪었나 이렇게 보면
So let's take a look at
사실은
the disturbance
통신회사나
in
이런 위성드론
2003.
회사에서는 문제가 생겨도
Communication
그거를 공개를 안
companies and
합니다.
satellite
왜냐하면
companies do not disclose
공개를 안 해야지
the
좀
problems
이렇게
they experienced
안정성으로
because
고객 확보에도 좋고,
it is
이거
related
문제
to
생겼다
the
그러고 그때마다
reliability. Whenever they
도움료도 올라갈 거고,
report the
신용 면에서도
faults
굉장히
they
떨어지기
experienced,
때문에
then
사람들이 다
it will
공개를 안
increase the
합니다.
premium for
휴식 면에서도
insurance,
나오게 됩니다.
and it will also
이거는
lower
이제
the
NAS
reliability.
미국 학술원에서
But
보고서에 나온 자료인데요.
this is the data from
내셔널 아카데미 오브 사이언스.
NAS, National Academy of Science.
이건 노스롭 그루만이라고 군수회사에서 모은 자료입니다.
And this is the data from Northrop Group.
걸 가지고 이렇게 보니까
It is a military
2003년에
company.
위성 장애가
In
생겼던 게
2003, there was a huge disturbance
알려져 있습니다.
in satellites.
그래서 여기 이제 2013년에 그 영국의
In 2003,
로열
in
아카데미
the
오브
US
엔지니어링 왕립
Royal Academy of Engineering
발표를 한 걸 보면
announced this
약
article.
2003년 기준 그런
As of 2003,
저기 폭풍 현상이 있으면은 약 10%의
when there
위성들이
was
장애를 겪는다. 것이 이제
solar
보고가
storm,
되고 있습니다.
around 10% of spacecraft experience
그런데 이런
anomaly.
10% 오는 게 2003년에 오고 지금 안 하면 뭐 20년 가까이
And
안
in
하는데
2003, we experienced this
그 장애 현상들이 계속
disturbance.
보고가 되고 있었지만 저게 대표적으로 큰
And it was a
아주 그런
major
사건들이 뭐 얼마나
disturbance.
자주 오겠냐 이런 걸 또 볼 수가
And
있는데,
people may ask how
저희가
frequently
요번에
we will
우리
experience this kind of events.
코비드 19 팬데믹을
Now we are
맞이하면서
going through the
그런 거에 대해서
COVID-19
좀 이렇게
pandemic,
주의가 커졌습니다.
and now
이
people
팬데믹이랑
are paying
스페이스
more
웨더에서
attention
심했던
to
이벤트들을 두 가지를
these
비교해
kind of
보면
events.
굉장히 유사한 점들이
When we
많습니다.
compare this space weather events and
대표적인 아까
pandemic, there
2003년과
are
같은 사례가
similarity.
여기 뭐 보면은
For example,
왼쪽 그림 중에서
on the left side,
파란 선이 아래로 내려올수록 이제 이게
when you look at the
이벤트인데요.
graph,
제일 아래까지
if
나와
the
있는 게
line is longer
1989년.
to the
그다음에
bottom,
오른쪽에서
it
2003년이
means
그 근처에
the event was
있는
bigger than the
이게
others.
큰 스톰이라고 봤을 때 이렇게 대강 지난 한 50년,
For the last
지난 세기 이렇게
50
보면 한
years
10번
or
정도
for the last
오도록 이렇게
century,
일어났습니다. 이제 팬데믹을 보면
there were around 10
팬데믹도
major events.
이게 뭐 여러
And as
가지
for pandemic,
그런 독감들,
there was the influenza, for example, swine influenza, SARS, MERS, and Ebola, and COVID-19. When we look at the major events, there were around 10 major events. So we can understand that there were a similar number of the events.
이거를 영국에서 보고서 그 재난
In the UK, there was a report
재해 보고서를
related to the
자연 재해 중에서
natural hazards.
X축은 확률.
On the x-axis, you can see the probability, and if it goes to the right, the probability is higher. And the y-axis is the impact.
확률이 제일 높은 자연재해에 맨 위에가 팬데믹.
So when you look at the top right corner, pandemic influenza is the most likelihood
여기서 발생할 확률이 앞으로 향후
events,
5년
and
동안
the impact
발생할
is also
확률이
very big.
5%에서 50%.
The possibility of having another pandemic is 5% to 50%. And this report was released in 2017. So actually 2 years later from this report,
확률은
the
비슷한데
pandemic
피해가
actually
두 번째로
took place.
큰 거. 물론 이게 스케일이 뭐 다섯 번째, 네 번째, 세 번째
And
이쪽에
they
있으니까 좀
used
피해 강도는 많이
the
틀리지만
scale of
그래도
1 to
대표적인
5.
그런 자연재해로 나와 있는
And
것이
another
스페이스
natural
웨더입니다.
hazard
굉장히 높다.
is a space
이게
weather
터진 지 너무
disaster.
오래됐는데, 불안하다. 그럼 보고돼 있어요.
So the report says that
그러니까
even
예언이 돼
though
있던 것들이 지금
the
우리
impact is
팬데믹을
lower than the pandemic,
봤었죠. 그러니까 이걸
still
스페이스
there is
웨더도
high
그만큼
possibility
경계를
of
해야 된다는
having
것을 알 수
another
있어요.
space weather disaster. So we
이건 이제
need to
2020년에
be
코로나가 터지고
cautious about
나서
this space weather
거기에 나와
disaster.
있는
After
보고서인데
COVID-19 pandemic,
여기는 뭐
they also
자연재해뿐만
released
아니라
another
형태가 좀
report.
틀어져가지고 뭐 사회재난, 뭐 이런
And in
환경재난,
this report, they included not
인정도,
just natural
사회재난 이런 거
disaster, but
다
also
나와가지고
environmental hazard
여기도
and
보면은
terror
스페이스
attack
웨더가
as
이렇게
well.
빨간
And
19번인데 이거는
number 19
향후
is
5년 동안에
severe
터질
space
확률이 아니라
weather.
내년
This
1년
is
동안에
not the
터질
prediction
확률이
for the next 5
1%에서
years,
5%다.
but for the next year. So the probability
결코
is
무시할 만한 그런 게
1% to
아니다.
5%.
우리가
So we should not
적은
ignore
확률이
the
아니다라는 걸 알고 있어요.
possibility of severe
국내에서도
space weather.
영국에서 이렇게 하고 있는데 국내에서는 어떻게 하고 있냐? 이제
Then what about
국내에서도
Korean situation?
스페이스 웨더에 대해서
In
최근
Korea,
들어서 많이 얘기를 하고
recently,
있지만
many people talk about
아직까지
space
굉장히
weather,
인지도가 떨어져 있고 그래서
but still the
이런 게
awareness is quite
자연재난에
low.
이런 게 있구나라는 게 알려진 지가 얼마 안 됐습니다.
It's been
이게 이제
only
작년
recent days
아마 스페이스 웨더도
when we
우리나라를
know
이렇게
about
걱정을
this
해야 되지
space weather
않냐라는 게
disaster.
2년
But
전에 여기에 이 보고서에 포함되기 시작했고
we included this
작년에
space weather
평가가
disaster
처음으로
in the report
이루어졌었는데요.
released 2 years
여기
ago.
보면 자연재난이 12가지가
When you look at
있는데
this report,
그래서 뭐,
there are 12 types of natural
이런
disaster,
태풍 같은 것도 있고 뭐
such as typhoon, cold weather,
황사, 뭐 지진,
heavy snow,
그중에
earthquake,
우주재난도
and
들어가
space
있고
weather
우주재난은
disaster was
여기에
included
재난으로 집어넣은
in this
근거는
natural disaster.
여러분이
And
어저께 그 발표에도 들으셨고
the rationale
우주전파
is,
센터의 어떤 그런
as you
설립
heard
근거도 되겠지만
yesterday,
전파법에 의한 그런 것들이
the
들어가
law on
있습니다.
radio
우주재난이
wave
언급은 되어
communication
있는데
was the
상당히
basis.
인지도가 약합니다. 그래서
And
자연적인
we
그런 뭐
understand that
엘니뇨랑 상관이 있지
the
않겠냐,
space
재난이
weather
이렇게
is related
그런 부분도
to
있고
the natural
아직까지
disaster,
좀
but we have low
객관적인 그런
awareness.
평가가 약한
So
편입니다.
until now, we don't
그
have
이 재난
much
중에서
objective
보면은
assessment.
이 X축은 인지도
The horizontal axis
얼만큼 이
is the awareness
재난으로서
level.
사람들이 인식하고 있냐
So
대중이라고 했는 그
how much
인지도를 보면
general public understand
가장
about this
인지도가
natural
낮은
disaster.
것이
And
이 우주 재난으로
the
해가지고 맨
space
왼쪽에
weather disaster, it has the lowest level
중간에
of
있는
the
맨 왼쪽에
awareness.
있는
You
것이
can find
재난.
space weather
물론
disaster on the far
발생
left side.
가능성은 여기
Of
뭐
course,
화산 폭발이나 이런 건 맨 아래 있지만
the
발생
volcanic
가능성은
eruption
그래도
is the lowest
이쪽에 중간
in
정도에 있죠.
probability.
그래서 외국에서 했던 그런 것보다는 아직 좀 차이가
Compared to other
나는 걸
countries,
알 수가 있어요.
we have lower
관련
understanding about space weather
전문가들한테 한
disaster
어떤
in
설문조사를
Korea.
하고 오직 과학적인
And
근거를 갖고 하지 않았기 때문에
this
이런
is just
좀
the outcome of the survey
대중적인
among
인지도에 의해서 많이
experts.
좌우되는 것을 알 수가 있는데 그럼에도 불구하고 우리가 많이 준비해야
Still,
된다라는 것을
I believe we
알
need
수가
to make
있습니다.
full
그래서 지금
preparation.
국가종합위험도에서는 굉장히
And in
최하위를
the comprehensive
평가하고
risk
있지만
assessment of
실제
the
외국에서 지금
state,
평가하고 있는 것과
it
굉장히
is
차이가
at the
있다라는
bottom
것을 알
of
수가
the
있습니다.
list,
예.
but
그래서 이제 그 에리오
it
위성들을
is
제가
still
많이
very
그
dangerous.
강조했었는데
I have been
이게 뭐
emphasizing
전리권이라고
the
부르는
space
그런
weather in the
큰
low
우주에
Earth
들어가
orbit,
있지만
and it is included in the
그
ionosphere.
부분에서 좀 많이 그 안에 자세하게 들여다보면 많이 차이가
But
납니다. 여기 이거는
when
세로 축은
you
높이,
look closer,
그리고 이제 이뭐
you can see
X축은 밀도입니다.
differences.
밀도.
So on
근데
the
그 중성대기도
vertical
있고
axis, you can see the
전기를
altitude,
끄고 있는
and the horizontal
이온이나
axis
전자,
is the
플라즈마,
density,
플라즈마
and
중성대기
ion
같이
plasma
보면
density is
밀도랑
depicted in
이런
the
것들이
graph,
굉장히 많이 차이가 난다는
and
것을
there
알 수가
are
있어요.
different
당연히 이제 위로
density.
올라가면
Obviously, when
밀도가
you go
떨어지겠죠.
higher,
그
the density will
중성대기
be
같은 경우.
lower.
근데 플라즈마인 경우는 안
And as
그렇습니다.
for
그래서
plasma, it shows
이
different
높이를 보면 일단은 여기
phenomenon.
파란색으로 이렇게 제가 밑에
There is
하늘색으로
an
해놓은
area
부분이
marked in light blue,
기존에 불렀던 전리층
and this is the
전리권의 대부분
ionosphere.
현상들이 이제
And most
여기서
of the
일어나는
phenomenons
그런
we can
기억이고
observe
위에 빨간 선으로 이렇게
take
표시한
place
부분이
here in this
위성,
area,
에리오 위성들이
and
올라가 있는 그런
the area marked in the dotted red box is
같은 전리권인데 높이
the
차이가
low
나요.
Earth
높이 차이.
orbit. So
그래서
it is in the same
기존에 했던 그런
ionosphere.
전리권에
However,
우리가
there are
전통적으로
different
했던 그런
altitudes.
연구들 이런 것들이
Conventionally,
과연
we
저궤도
carried out
위성이나
study
거기다 높은 그런 지역에
for the ionosphere. However, we need to ask whether the outcome of the research can be applied to
여기서 이제
the satellites
프로파일의 특징을
on
보면 전자
LEO.
밀도가 제일 높은 부분이
When you look at the profile,
여기
F has the highest
낮은
density,
부분, 거기에 그 왼쪽에서 이렇게 들어갔다 나온 부분에 보면은
and when you look at
그 일렉트론
300 kilometer,
그런 지역을 알 수
electron
있는데
density is the highest,
대기 밀도, 중성 대기 밀도는 점점
and the
줄어들어가지고
density of
위성
the neutral
고도에까지
gas
올라가면
is
거의
going
뭐
up,
전자 밀도 5도로 굉장히 이제 희박해집니다.
and
반면에
in the high altitude,
전통적인 전립 측영역,
the density is low. But
중성 대기 밀도가
when you look at the
전자
ionosphere,
뭐 100만 배, 10,000 배, 100만 배 더 여전히 큽니다. 그래서
still the ionized gas density is 100 times higher than the natural gas.
이런 외부에서 어떤 섭동이나 들어가거나 하면
And if there is external shock, then there will be changes in the current. These currents will be generated within 100 kilometers in the ionosphere area. So the 400 kilometer area is not relevant. We call this 100 kilometer region as a diamond region, and we need to do the modeling for this area. And I believe low altitude is not relevant. So even though it is the same ionosphere, depending on the altitude, and there are differences. So we need to look closer in detail. And there is a radio occultation.
그냥 RO라고 부르겠습니다.
In short, we call this RO.
이거들은 보면 위성에서 지상으로 하는 게 아니라 위성과
So
위성 사이.
this is used not between the Earth and the satellite, rather it is used between satellites.
위성에서 위성 지나는 동안에
So when the signal is sent from one satellite to another satellite, it is monitored, and the electron density was higher in 400 kilometer area. That's why RO is higher in that zone. And in other zone, there is no change in RO.
RO에서 나오는 그런 신호가 보여주는 그런 높이보다 훨씬 더 높이 있다.
So the satellites are located in the area higher than the RO. When you look at the left side, you can see a diagram, and RO is used for monitoring. However, the central area is 200 kilometer, and it is not the changing value from the satellite. And we use multiple models to cover the planet. We have the geospace model, and the important area is the area where current is generated. And it is around 100 kilometer altitude, the dynamo region. And the boulder is the change in 100 kilometer. It does not show 500 kilometer altitude. When you look at the satellites using a radio wave, obviously this model will be affected by huge change. However, it does not show the change in the satellite itself. What we want to know is the impact to the satellites in the LEO. If we have satellites around the globe, and if we have the capability to monitor the space weather, then we can obtain good information from that. And in the future, the number of the satellites will be tens of thousands of satellites. So this information will be required in many regions, and there will be lots of application. This is a video, but it is not played. From the satellites, we need to make the measurement and observation. then we can understand the current status of the satellites. In the new space age, we need to have that kind of model. In the past, we used RSG, for example, solar X-ray, solar high energy particle, and geomagnetic field. However, those observation will not be enough to understand the status of the LEO satellites. In 2003 event, 10% of the satellites were affected. So we need to understand in which region, what kind of satellites were affected, but we don't have that information at the moment. So in the future, obviously, we need to improve the lacking information in the future research. And I've been introducing many information, but it is not my opinion. I was actually from National Academy of Science and National Academy of Engineering from the US. They released lots of reports warning that we need to prepare for the future event. And one of the authors is Thomas Jurbuchan. He is a leader in NASA. So after releasing this report, he moved to NASA. And he also published a book. And when you look at the conclusion of this book, he says that we need to have a small CubeSats, and those CubeSat constellations can be created to provide space weather information. And if that is possible, then it will be very useful to study space weather. This report was released 5 years ago. As several years ago, in the COSPAR, the similar idea was suggested. Using small-scale satellites, we need to understand the space weather. So, in conclusion, we can compare space weather event with pandemic, and there is high likelihood of having another space weather disaster, and the impact is very huge. And in the fourth industrial revolution era, we need a responding system. And the number of the satellites in the LEO is increasing rapidly. And this technology will be very useful for economic activities. From several years ago, Korean Space Weather Center is promoting the small satellite constellation, so it will be very useful in the new space age. And I believe this is a very important topic in leading the space weather area. Thank you very much. Professor, thank you very much for the presentation. We are behind the schedule, so we will skip the Q&A session, and please leave your question in the chat box on YouTube, then we will hand over the question. Thank you very much.
Now we're going to listen to the last presentation of the morning session. The speaker is Mr. Kim Kwang-hee from the Satellite Wave Monitoring Center. Please welcome him with a big hand.
안녕하세요. 저는 그 위성 전파
Good morning.
감시센터에서 위성
I'm
전파를 감시하고 있는 부서의
Kim Kwang-hee. I'm in charge of the
일단
satellite wave monitoring at the Korea Satellite Wave Monitoring Center.
위성 전파 감시 이런 부분에 대해서 말씀을 드리게 됐는데요.
So you may wonder why I'm talking about the radio monitoring in Korea, but you all understand that satellite is an artificial object. It is registered with ITU according to the UN convention, whether it's for weather observation or communications. It needs communication with the Earth station, and the communication we use is the radio wave.
우주전파환경도 전파법에 따라서 우리가 이제 예측을 하듯이
We conduct space weather forecasting according to the Radio Wave Act.
국가 자원이면서 세계적으로
The radio waves are national assets, and it is also regulated by international rules and regulations. That's why we register our satellites with ITU, and we are also conducting radio monitoring according to the Radio Wave Act. Since we are behind our schedule, I'll skip some of the slides and try to summarize the content of my talk. I'll skip this slide. I'd like to briefly introduce the Satellite Wave Monitoring Center. Since 1990s, Korea began its satellite development effort. And from Korea Sat-1, we've launched our satellites, and Korea satellite was also launched after many years. And since 1990s, we've been developing our own satellites, and we used to have only US and Russia developing their own satellites, but in the period, other countries started to join the competition, and France, Japan, and the UK also launched their own satellites. And for the first time, Korea became the 5th country in the world to open its satellite radio monitoring center, and there are 14 countries that operate the monitoring centers, and there are 194 countries under UN, and only so far 14 countries have the satellite radio monitoring centers. Some countries have their own satellites and others lease other countries' satellites. In 2002, in August, the center opened and began our work on geostationary satellite monitoring. And in 2016, we also initiated our business of non-geostationary or low Earth orbit satellite monitoring. When it comes to the geostationary orbit satellites, our scope of monitoring is east 55 degrees and to west 160 degrees, which is from the Seychelles Islands to the Hawaii. There are 119 satellites, both domestic and overseas, that we monitor. And we have 2 monitoring stations. One monitoring station has the antenna with the diameter of 13 meters. You have one antenna, and that covers the entire band. So with monitor 1, they monitor Mugunghwa and Charlian series satellite, and with monitor 2, we have scheduled, and mostly it covers the domestic satellites. As was discussed in the previous presentation, you see we are increasing the number of satellites that we monitor. When we began our operation in 2022, we monitored 77 satellites. In 2012, 98 satellites, and our monitoring capabilities increased by 30%, and this year we monitor 119 satellites.
따져보니 3만 1,000기 정도가 됩니다.
And so far, we've monitored a cumulative number of 30,000, more than 30,000 satellites.
이걸 한번 3만 1,000기로
So,
쌓아보니
to stack all the satellites that we've been monitoring, considering the average
이성들에 대해서 감시를 하고
height of the Koreasat 5, which is about 3.4 meters in height, if we stack all the satellites that we've monitoring, it equals to 12 Everest mountains put together on top of each other. Now, speaking of the non-geostationary satellite monitoring,
지금 현재 저희가 그 한반도 상공을 통과하는 이성의
there are
숫자는
satellites,
약 5,800여 기 정도.
there are 5,800 of them that fly over the Korean peninsula.
한반도 상공을 통하면서 전파를 쏘는
And the ones that emit meaningful signals amount to around 670 satellites. And we follow the orbiting schedule of the satellites, and there are 4 stations that monitor these non-geostationary satellites. So we have monitor 3 to 6. With monitor 3, it has non-directional antenna. And monitor 4 monitors amateur satellites up to 1 gigahertz, and monitor 5 monitors the entire band, and monitor 6 monitors L band and X band. In the previous session, the speaker talked about the increasing number of satellites and the necessity of monitoring such satellites. We began our non-geostationary satellite monitoring in 2016. The number of satellites that we monitor increased by 6 times, so we now monitor more than 5,000 satellites. And we also identify a lot of satellites that are being added every year. And by 2030, we are going to have LEO satellite communication that will be the main source of or main usage of the satellite communication. We estimate that 200 satellites will be launched on non-geostationary orbits. So, once again, we remind ourselves of the importance of the non-geostationary satellites. I wanted to show you a video, but I'll have to skip because of the time constraints. We provide radio monitoring activities, and that is related to the satellite operators. And this is critical to protect the critical telecommunication network, and we also conduct surveys on the operation of the ground stations. There are about 330 organizations that have to receive satellite radio waves, and for them, it is critical to prevent the source of frequency jamming. There is also ChinaSat and Japanese satellites, and that is close to Korean satellites, and we have to see whether there is any spillover, and we have 18 points of locations in the Korean peninsula to collect data to understand whether there is any spillover from any nearby overseas or foreign satellites. Of course, there are frequency jamming that often occurs, and we can detect the source of frequency jamming by looking at the time difference of arrival and frequency difference of arrival. So we analyze these data, and this is used to prevent and detect in advance the possible source of frequency jamming.
그 혼신은 좀 지금까지 한 180여 건 저희가 처리를 했고요.
So far, we've dealt with 180 frequency jamming cases. In 2018, we began our frequency jamming source analysis system, and since 2018, on average per year, we deal with 20 frequency jamming incidences. Before 2018, we were able to analyze and eliminate the source of frequency jamming only when there is a report on such frequency disturbances. But now we have a capability of detecting the potential of frequency jamming in advance.
이성이 증가하고 있고
Now that we have increasing number of satellites,
혼신도 꾸준히 늘어나고
and frequency or signal interference is taking place more frequently, and that's why the Satellite Wave Monitoring Center analyzed the relevant data and take proactive actions in order to prevent such event.
나사 이성에 우리 군에서 쓰고 있는 파수가 영향을 준 사례입니다.
There was a case whether NASA satellite interfered with the Korean Air Force radar.
이호도 EA 같은 이성도 해당이 되는데
This is a case with the Chandrayaan-2A satellite.
무궁화 5A 이성이 주로 이제 뭐 우리 군이나 해경에서 주로
Usually the Korean military and the Navy uses the KoreaSat-5 satellite for their own communication.
지향을 좀 잘못해서
Sometimes there is an error with the orientation with the overseas or foreign satellites, and interference was occurred. And another case was that
주변에 이제 우리 그 지구국이 있고
there was a ground station,
그
and
옆에 이제 주변에
nearby there was a telecom
이 이동통신 신호가
signals, and that telecommunication signals
이렇게 유입이 돼서
enter the satellite uplink signal,
관제하는 쪽에 통신에 이제 그 통신을
causing frequency interference with the command center.
이런 부분들을 저희가 이제 잘 조사하고 분석해서
These incidents are investigated and analyzed, and we work to eliminate the potential sources of frequency
저희가
interference.
이제 이 국가적으로 주요한 이성 관련된 이런 행사 시에도 전파 보호 활동을 하고 있고요.
We also provide radio wave protection activities for important national events.
발사 현장에서도 저희가 이제 발사 전하고 발사 후 이렇게 관제용 주파수 또는 그 이성에서 내려오는 발사체 신호에 대해서
We also provide services before and after space launch vehicle launch.
이렇게 다누리호가 이제 발사가
The Korea
됐었는데
Pathfinder lunar orbiter was launched in August this year,
여주에 있습니다. 시무주 주구구에
and we have the Deep Space Network in Yeoju area operated by Korea Aerospace Institute, and the antenna is about 35 meters in diameter.
70년대에 되어진 금산에 있는
The Kumsan Space Center
이성 통신을 하기 위해서 세워진 안테나가
antenna
33m입니다.
that was established for the first satellite communication was the biggest, with 30 meters in diameter. This was made in 1970
상징성이 있다 보니까
for Kumsan antenna
국가 등록 문화자로 지금 등록이
because
되어 있어서 관리가 되고
it's quite significant and has a special historic meaning. It is designated as a national treasure.
중첩이 되어 있습니다. 이제 그러다 보니까
We also provide a radio wave protection service in order to ensure there is no frequency jamming,
이렇게 가끔 이렇게 전파
because
훈련 상황이 됐을 때는 이제 신호가
there is an
유입되는
overlapping
상황에서
between the
발사 전, 발사 당일 또 발사
control
후에도
frequency
저희가
and the frequency
그거를
used by the military.
주파수는 지금 모니터링하고 있습니다.
So we enhance our monitoring activities so that on the launch day there is no frequency jamming. And this is the last part of my presentation. Now that
지금 올라가는 이성들은 훈집 행태로 이루어지고
there are so many small CubeSats that are being launched as part of the constellation,
확보하는 차원에서 지금 이제 현재 비정기 전파 감시 시스템을 고도화하는 작업을 하고
it is
있는데
critical that we further sophisticate our monitoring capabilities for the non-geostationary satellites. Our goal
선거를 통과하는
is to analyze
사이에 적어도 5개 이상은
least 5 satellites in a real-time basis that flies over the Korean Peninsula every 10 to 15 minutes. Now that we should be prepared for the LEO satellite communication, we will continue our efforts to improve our frequency protection services so that in the event of any frequency jamming, we will make sure that those events are prevented in advance. With that, I'll conclude my presentation. Thank you very much for your attention. Thank you very much, Mr. Kim, for your wonderful presentation. Now that we have a lot of satellites in the air, the activity of the Satellite Wave Remote Center will be even more important. Now that we are running out of time, we won't be able to take questions from the on-site participants, but if there are any questions that are posted online, we'll make sure that those are delivered to the speaker. With that, we'll conclude the session 2 of this morning. I would like to once again thank all the speakers and participants for their kind contribution to this conference. Thank you. I would like to also thank Mr. Park Ji-yoon for kindly moderating the session, and I'd like to once again thank all the speakers of the morning session. Well, this wraps up the morning session of our conference, and after having a lunch break, we'll move on to the session number 3. Thank you.